So in this part I am going to discuss about floating point number representation and its standard. I mean IEEE 754 standard. So as part 1 I have discussed many types of number system. Here I will discuss the floating point numbers presentations. Well, so here is a basic syntax for the floating point representation. Any number having a decimal point we call the floating point number. 5.2, 3.5 is an example of a floating point number. Well, so the basic syntax for a floating point number is plus minus significant times base to the power exponent. So the part significant is also known as mantissa or the coefficient. So in this lecture I will call all the terms significant, mantissa or coefficient, but be careful, these all are same. Well, so we know the basic syntax is plus minus significant times base to the power exponent. Okay, so let's have an example. 10.45 times 10 to the power 44. So let's extract this significant, base and exponent from this example. So this part 10.45 is significant. So this part 10.45 is the significant or coefficient or mantissa of this number. So here the base is 10 because we put it 10 and the exponent is 44. So always in our calculator or digital display we used to see this type of number representation where there is a significant, there is exponent and there is a base. So base 10, as I said in the part 1, base 10 is for decimal, base 2 is for binary, base 8 is for octal, and then base 16 is for hexadecimal, whatever. So this is the base. So now the question is why we need this format to represent? Why not we just represent the number? Well, the answer is if we want to represent a very small tiny number like this, 0.10, a point followed by 10 zeros and then 5, it takes a lot of memory space to represent this number into binary. On the other hand, if we take a very big number like this, it also takes a lot of memory to represent this number. So this presentation for a floating point number, it takes only few bits. For example, to represent 10, we need 3 bits. We don't need to represent the base because for a specific format, base is already defined. And to explain this 0.5, we need only 3 bits. So with the 6 bit, we can represent this number, whereas if we want to represent this number, it takes huge number of bits. So one reason we find that to make this format is to take the less memory space in our where we store the number. Well, so after basic syntax, now I would like to explain how we can represent a number. Although there is a basic syntax here, but following this basic syntax, it is possible to make in many ways. Here is an example. This number 0.123 times 10 to the power 4 or 0.0123 times 10 to the power 5 or 1.23 times 10 to the power 3, these all number having the same meanings based on the definition that we discussed the earlier slide. So what will be the solution? The solution is we need the normalization. The first normal form is the integer part should be the 0. So here you can check the integer part is not 0. Yeah, here integer part is 0 here, integer part is 0 here, but here is integer part is not 0. So we eliminate this. And the second part of normalization is the after decimal point the digit cannot be 0. So here you can see that after decimal point there is a 0. So the remaining this part 0.123 times 10 to the power 4 is the normalized form. Well, so we have a basic syntax, and within the basic syntax we have the normalized format for the floating point number. Well, now we're gonna discuss about the formats, I mean length of the floating point number. So here you are, there are two formats. Right? One we call the single precision format that have exactly 32 bit. For example, once you do program in C language, you have to define a data type to store some value in a variable. If you define a data type whose name is called float, it occupies a 32 bit storage for a memory. That means it's a single precision or 32 bit floating point number. The same thing is the double precision, 64 bit. Now the last part of the question is, well, we have 32 bit, but how we segmented this 32 bit into the basic part, what will be the exponent, what will be the coefficient, and what will be the sign part. So this 32 bit or this 64 bit basically segmented into three parts. So one is the sign part, which is indicating the negative number or the positive number with a single bit, and we have the biased exponent. I'm letting you know the why biased exponent, and then remaining part we have our significant or mantissa or coefficient. Well, the recap for you, we have a basic syntax with normalized rule that we have significant times base to exponent, and we have a format 32 bit and 64 bit, and each format having sign, biased exponent, and the significant mantissa or the coefficient. Well, so now let's talk about why we need the biased exponent. Well, so let's consider we have 1 bit for sign and 8 bit for exponent and the 23 bit for coefficient for a single precision or 32 bit number. So as you know, the exponent could be either positive and negative. So in 8 bit we can write maximum 256 positive value, but we need to make a positive value and as well as the negative value. So we have to divide the value within range 128 to positive 127. To do that, the base for this 32 bit is defined to 120 or 127. And how it comes, for example, if you would like to make this number, your exponent is -3, that means the value of the exponent should be 124. And how the 3's come? This 124 is then subtracted from 127 and you will get the -3. So you don't need another sign bit for the exponent part to represent the negative number. So using the biased value, you will present both the negative and the positive number. Well, these are the basic thing, but we need to standardize this part and what is altogether defined in a standard that we call IEEE 7.4 And here you are. IEEE Standard for Floating Point Arithmetic, or IEEE 754, is a technical standard for floating point arithmetic established in 1985 by the Institute of Electrical and Electronics Engineers. So the main objective was why we need a standard, because in that time the hardware manufacturer or software developer defined the floating point number in different ways. As I said in earlier slide, in many ways is possible to represent a floating point number in both software and hardware. So this standard is targeting both the software implementation and the hardware implementation. This is the first thing. And it having three revisions till now. Once in 1985, and then it's revised to 2008 inclusively to implement the decimal floating point. That is our discussion about part 3, and a minor revision in 2019. So this standard, as I said, is established because of the reliability and the portability for the hardware floating point unit. So the hardware manufacturer and the software developer and the other compiler guys, they can make a compliant way to develop their systems that can easily portable. In the standard, there are the formats, the interchange format, and the rounding rules, operation and exception handling, all the things that cause having many problems for the different types of variations is possible, that are identified and standardized with the format. Okay, let's go to the board and then we will discuss a bit detail for the binary floating point presentation. Have a look with the standard. As I said that our standard is IEEE 754 for the floating point number. So according to the standard, we have two types of presentation. One is single precision, that is 32-bit, and another is double precision, which is 64-bit. So within each precision, there are three segments. Here you can see the three segments. One is we call the sign, and then exponent, and the mantissa or the coefficient. Here is as well sign, exponent, and the mantissa. Now let me tell about how many bits are allocated for each of the segment. In single precision, the sign is 1. In double precision, the sign is 1 as well. For single precision, again, the exponent is 8-bit. And in case of double precision, the exponent will be the 11-bit. Finally, the coefficient for the single is rest of the bit, 23 bits, and here is 52-bit. Okay, so we have two types of presentation: single precision and the double precision. Single precision having 32-bit, double precision having 64-bit for each number, and we have a sign, exponent, and the coefficient for each of the presentation, and we have different number of bit for each precision. Well, and here you are is the expression that is representing for a floating point number. X floating point number 32-bit, x floating point 64-bit. The equation is same, minus 1 to the power s 2 times exponent minus 1 to 7, and then 1 times c, coefficient or the mantissa. Here the only difference is for the single precision, this number is 127, and for the double precision, this number is 1023. Okay, let's discuss with the example. So I would like to pick a number, for example 4 0 4 0 0 0 0 1 2 3 4 5 6 7 8. So this is a hexadecimal number. So as you know, each of the hex number having 4 bits. So there are 8. So 8 times 4 is 32 bit. Let's make it binary. So 4 is 0 1 0 0. Then this 0 is here, and then again 4 0 1 0 0, and then 1 2 3 4 5 zeros. 1 2 3 4 and then 5. Well, so what I would like to do, I'd like to make the segmentation for this number, right? Okay, so here is the first bit is represented as a sign bit, and then count the next 8 bit. 1 2 3 4 5 6 7 8. Here you are. So this is our exponent, and the last rest part is the mantis or the coefficient. Let's put the value in this equation, like say equation 1. Okay, so we have now the result will be, we have x floating point 32 bit representation for a number is equal, so minus 1 to power s is here 0, so put it 0 here, times, so here is our exponent. Calculate the exponent and put the value of exponent here is 128, because the value of this part is 2 to the power 1 2 3 4 5 6 7 is 128, minus this is 127 is this number, I mean this is from the formula, times 1 into the coefficient is the after point, so it will be the 5.5. Okay, so now calculate the exact result. Anything power 0 is 1, and then 2 times 2 to the power 128, 2 to the power 1 times, so here we have 1.5. So 2 times 1.5 is just equal 3 is the decimal number. So now let's recap a bit from the here. So we saw what are the presentation of 32-bit number and what are the expression for this number here. This is the expression, and finally we saw an example here. This is a number, and we convert it to the binary and calculate the decimal number. Well, so this is a presentation for a decimal floating point number. And now we will move to the decimal floating point arithmetic on a presentation slide. Okay, so till now we know the standard of floating point number. We also know a floating point number having 3 parts: the exponent, sign, and the coefficient or significand or mantis. Now we will try to study the basic operation of those floating point number. Here in this part we will discuss about the addition, subtraction, multiplication, and division. Let's take the pointer again. Okay, so as we know that a floating point number having sign, exponent, and coefficient. So what will be the result after addition or subtraction? The rules of addition is, first we need to adjust the exponent. Before doing the addition, the exponent need to be adjusted. So we called it exponent alignment. If the exponent of 2 operand is same, we don't need to do this operation. But if the exponent of 2 different operand are different, So we have to align with the smaller exponent and change the coefficient according to the alignment. We will show it in the whiteboard example. Later, we need to add or subtract the significant or the coefficient or mantissa. This is the add or subtraction operation. Finally, we again need to adjust the exponent and the normalization. As few slides ago, I showed that every single floating point number have to have a unique representation, so we need to normalize before the result. And there is another thing, if necessary, we need to perform the rounding operation. In case of multiplication, it's pretty simple. So we just need to add the exponent for the multiplication and subtract the exponent for the division. And then we need to perform the multiplication operation or the division operation of the coefficient. Finally, we need the rounding. Well, here you can see, so the result after a floating point operation, the result will also a floating point number that having sign, exponent and the significant. Okay, so the rule I discussed in the last slide, here I summarize all for you. So let's again recap what the sign of a result. In case of multiplication and division, the results will be, the sign bit of a result will be the exclusive OR of two operand. In case of addition and subtraction, the sign bit calculation is pretty difficult, but the common rule is the operand having the larger absolute value, the sign will be the same as the operand having the largest absolute value. There are two numbers, I mean 5 minus 2, so the 5 is largest and the sign of 5 is positive, so the result will be positive. And now how we calculate the exponent. As I explained last slide, in case of multiplication, the exponent of a result is just addition of two exponents. In case of division, we need to subtract this division. But in case of addition, as I said, you need to align first and then finally you need to normalize the exponent. In case of subtraction, it's same. You first need to normalize and then you need to align. So the significant of a result is basically the main operation. So in case of multiplication, we need to multiply the significant. In case of division, we need to divide the significant. In case of addition, we need to add the significant. Similarly, in case of subtraction, we need to subtract the significant. So this is the basic rule that also defined in our IEEE 754 standard, and this following this way every computer are doing a floating point operation. So to make it more clear, I will show you an example in whiteboard. Let's move to the board to find the hands-on example. Okay, so we have two numbers, A and B. A is 9.75 and B is 18.5625. Well, if you convert it, so this is the number that we have, A, and this part is the coefficient and this is the exponent, and also for B, this part is the coefficient and this is the exponent. 4. The first thing we have to do, as I said in the slide, align the exponent, because here is 3 and here is 4. So this exponent, I mean this operand A, need to be aligned with the operand B, because we can only perform the addition or subtraction if both operands exponent are same. So let's newly write A again. Then A will be 10.1001110 into 2 to the power 4. Now the exponent here and the exponent here both are same, so we can now calculate the addition operation. Well, so now we need to add the coefficient. So the coefficient of A is 0.1001110, and the coefficient of B is 1.00101001. So simply add it and we will get the 1.11000101. So this is the result of coefficient, and the exponent is 4. So the result is A plus B equal 1.11000101 times 2, 4. So the steps are, we make the alignment and then we make the perform the addition, and this will be the revision. So you don't, the format is already in the normalized format, so we don't need to be normalized again. Okay, so if you want to put it in our standard format, so what we have to do, we have a sign, we have a biased exponent, and we have the coefficient. Okay, the sign is both are positive, so it will be the positive. The exponent here is 2, and we have a bias of 127 plus 4, it will be the 131, and this coefficient will be replaced here. So the result is like this for addition. Now come to the multiplication. More simple example. Don't care about the, for example, A is equal 3. I make it binary, I think. Make it binary, it's more easier. One point 1.11001 times 2 of 6, and then 1.1010 times 2 of minus 3. So here you can see the exponent of both A and B are different. So regardless of this, we just need to add the difference. So we have to make here is the V, so we need to make the result A times B will have a exponent, will have a coefficient, and have a sign. So let's example, this is positive and this is negative. Okay, so exponent will be the add of this exponent, so 6 plus minus 3 equal 3. The coefficient will be the multiplication of these two terms, so put this term 1.1100 times 1.1010, and the sign is the XOR of A XOR B, sign of A XOR sign of V, in 1 XOR 1 is equal positive. Okay, so according to our format, sorry, it will be 0 for positive. So our sign is 0, our exponent is here, exponent, the new exponent is 3, so put the 127 plus 3 again, 131, and this part will become to the coefficient. So this is the way that we can do the multiplication and addition. Similarly, you can do the division and subtraction. Well, let's